A lot of this content is going to be very similar to 225, 233. Well, not 225 this time. 233, not really 241, but I guess you could pull in some concepts from there. And then it would be, I think it's one of the EC classes. I want to say one of the FPGA ones, or like 110, 210, something like that. So, all right. So today's agenda, we're going to be covering not binary operations, but everything else. So CPU, RAM, GPU, motherboard, storage, and then I say chip design fabrication, but that's really just like, so you guys know what like FPGAs are and ASICs and stuff like that. So those are really more the 233 and lower level system, EE. Okay. So I am not an expert on this. I'm not an EE major, but so, you know, some of this is through my classes, some of this is through my own like research. So I may have like certain things I remember wrong. So do like correct me. That way we can all learn. And if you guys didn't know, that Latin phrase at the end there is our motto, Superior Aude. Does anybody know what it means? Yeah, go ahead. Yeah, dare to know. Yeah. I think some other universities have it as well. Yeah. So I don't know. It's like, it's pretty cool. You know, I wrote that. I'm like, wait a second, you know, perfect place for a motto. So you guys might be familiar with this. This is if you guys, you know, have a gaming PC, that's what it's going to look like. You guys might already even know some of the parts. Some of you guys who have bought pre-builts might not know the parts. But a lot of what's in here, we're talking about the CPU, the RAM. You can see the RAM sticks there, right? The GPU, the motherboard, right? The PC, the CPU is underneath that fan right there, the middle fan, right? And then there's a case, there's a power supply here. And then, yeah, I think that's about it. And maybe you have some hard disks like tucked away either here or back there. But I don't see any. A lot of what's in here is the exact same in the server side, except the server side just has more of it. And because they need to scale and they have so much, they actually have these entire racks. So you can see the racks over here, right? This is how they put the computers in. The computers look like this, right? So look at that compute node right there. You basically slot that into a rack. So that looks like a half rack setup, right? So it only takes in like half of the rack space, the width. And then there's a standardized version of the heights of these racks, right? So each sort of unit of the height is around 1.75 inches, I believe. And so we call that U. So a 1U rack is 1.75 inches height with the full rack width, right? And then of course, like the depth is the same or whatever. And then a 2U rack would be whatever 1.75 times 2 is, right? 3.5 or something like that. Yeah, 3.5 like inch high rack like that. So that looks like maybe a 2U or a 3U. You can't really tell. That one would be a 1U rack, right? Looks only like 2 inches roughly, and that one might be like a 3U rack, right? So that's how we do server racks. And the server racks just allow you guys to basically put a lot of like components inside one thing and just slot it in wherever. So if you want to change from one rack to another, it's very hard to do like something on this PC. You'd have to take it all apart or whatever. Here, you just unplug everything, you just slide it out, right? Or you unscrew some stuff. You slide it out, you slide it in, screw it back in, plugs everything back in, right? That's about it. So it's modular, right? That's what it's for, and highly scalable. But the concept that we learned today about the personal PC, which is the exact, you know, it's going to be the exact same as the server side. So not to worry there. All right, motherboard. So we're going to start with the motherboard. Motherboard, you should think about it as literally a place for all your toys. And it's where you put your CPU, your GPU, you know, well, I should say your PCIe slots. And then it has certain chipsets as well to make like USB ports, open IO, stuff like that. Oh, shoot. So here's a motherboard I was looking at actually buying for Quant. I just took it offline. I've highlighted each of the components of at least the important components of a motherboard that you should at least know, right? So we're going to be talking about what, like, if you don't know what CPU RAM CPU RAM or M.2 is, that's fine. We're going to be talking about that today, but I just want you to sort of get like a sense of how everything is covered here, right? And the layout of everything. So if you look here, right, the RAM is very close to the CPU, right? And there's a call to that, right? Literally the distance in the wire from whatever you're trying to go, from wherever you're trying to go to, right, that actually matters a lot. You get latency there. The longer the wire, the higher latency. We're talking about, even though it's speed of light or the speed of the electron, so to speak, right, or speed of wire, right, it's going to be, you don't want that extra latency there, right? You already get enough latency within the actual like modules itself, right? You guys should be familiar with some of these there. So if you guys look there, it's a bit, sorry for the bad picture, but you have an Ethernet port right there that I'm pointing to. And then like four, it looks like USB 3.1 and 3.2 ports there. I don't know which one, right? You can see like an HDMI port all the way up there, and also a I forgot, a display port, DP port up there, right? What's that going to be for is the integrated graphics within the CPU itself. So that each CPU actually has an integrated graphics nowadays, I believe, unless you're doing like server side. I don't know if the server ones have. And then you'll see that there's a special highlighted one, not really highlighted, but this, even though there's another one that is as long, I don't know if you guys see it, there's two that are as long as that X16 slot right there. That one is specially like colored because it's actually the one that the CPU directly controls. Now you can't see over here, and honestly, I don't know where it is, but there's a set, there's a set of chips, probably in like some area, like a chipset, and the chipset is in charge of handling I/O into this USB port and handling maybe the other PCIe ports, right? So we're going to talk about that in a second. The other thing I want you to look at is the RAM DIMM slots. You'll see that each of them are alternating colors. The colors actually correspond to dual memory modules. I think that's what it's called. Where if you slot it in at both, like in the same color, right? So alternating, like 1, 3, or 2, 4, then you can actually pull double the data. Okay, so it's pretty cool, but just wanted you guys to know this is what a motherboard looks like. You guys should be able to identify what each component is doing and what it does, right? CPU sockets where you put your CPU. M.2 slot. Well, that one has like a plate covering it for, I guess, looks. I don't know if it actually does anything for cooling. And then there's one more here and another one, a smaller one here. That one is for storage. So it's a new type of storage form factor. Okay, M.2. It runs on actually PCIe as well. PCIe is a type of bus, so similar to this one. It's just that different form factor, and those are for NVMe. Yeah. So I don't know if you can actually put SATA ones on there. I don't know if there's any SATA sticks like that. And the last one, I guess I forgot to put an arrow here, is these 4 are SATA ports, and then there's actually 2 more over there. So there's a total of 6 SATA ports on here. SATA port is just like a PCIe, but it's way slower. It used to be for hard drives, like spinning disk ones. We'll talk about that today. SATA is just like, I think maximum is like 500 megabits. I want to say 500 something. And then PCIe is like 10 times that or something like that max. Depends on which gen though. I don't remember the numbers off the top of my head. Okay. So for motherboard, this is what it used to look like. Okay. We're going to talk about the north-south bridge. So the North Bridge was in charge of basically anything that was important for the CPU that the CPU needed. So that would be like connecting to that first graphics accelerated PCIe X16 port, right? So the one that is specially colored up there, that's what it would connect to because it's graphics, I believe so. Graphics accelerated, right? And then it will connect to the RAM and then connect to the South Bridge. That's really what it was in charge of. And that's because in order to get RAM, your CPU would have to go through the North Bridge, get the RAM, and it will have to come back to the North Bridge into the CPU, right? So what's good about this is there's something called, I think, what is it? Uniform memory access, right? Where that the latency you get from any, like if you had additional CPUs, right? The latency you get from each CPU to the RAM is going to be the same, right? There's not going to be any difference. That's what is good about this setup, right? But the problem is you get like, even though it's the same latency, you get a higher mean, right? You get a higher latency because you have to go through the North Bridge, right? And then, there's a clock that has to deal with that. And then I guess if you want to go to anything else, you'd have to go through the North Bridge into the South Bridge and then to access anything else. So that's like USB port, right? Flash BIOS. BIOS, you don't really care, right? PCIe, right? Any other PCIe slots, right? So if you're doing high frequency trading, right? And you have like a network card or whatever that you're, or 2, right? And you follow this sort of like design, but this is a pretty old design. It's like probably 10 years old at least. then, in order to just get to like one of the other network cards, you'd have to go CPU, North Bridge, South Bridge, PCIe slot. Whereas if you, just wanted to go in, instead of the graphic card slot, you put like a PCIe or some other network card or whatever, right? You go to CPU, North Bridge network, right? It's sort of one hop less, which is, of course, faster, right? And then I guess, so as a result of eventually what you'll see as system on chip CPUs, right, we actually get rid of this architecture. But I'll talk about system on chip CPUs later. Yeah, and yeah, stuff is that. All right, so now so it used to be North-South Bridge architecture and SMA. I forgot what SMA stands for. It's in the notes if you guys check for it. We actually, I think it was 10 years, roughly around 10 years ago, we transitioned to NUMA architecture. NUMA stands for non-uniform memory access. Okay, so it probably sounds a bit worse because it's non-uniform, right? Why would you want non-uniform memory access? Well, what actually happens was we converted to system on chip CPUs, where the CPUs themselves on the actual like die have like a memory controller, have a PCIe controller, right? And so instead of actually having to go through the North Bridge and access the RAM, each CPU itself would access the RAM directly, much faster, right? We're talking about like, I think like drops of, I don't even know, I don't want to say any like numbers off the top of my head, but it's much faster, right? From accessing, having to go through the North Bridge. And it's easy to scale, right? Each CPU sort of has its own piece of local RAM memory that it uses. But the problem comes up when you actually have to use more RAM than your CPU will do, or even more, right? Like just access some other piece of memory, right? Then you would have to go through the other CPU into their RAM, right? So if you look at here's the rough like boundary for clock cycles. There's a source for this on the notes on the speaker notes, right? L2, L1, L2, L3 cache. Okay, fine, right? If you look at the difference between accessing your local RAM 190 to your remote RAM, right? That's 120 cycles more. 120 cycles, you could do 10 like L2 hits, right? Like that's pretty bad. And if you're doing a high frequency application, we're talking about we really want to hit L3 cache, right? Like maximum, right? We don't even want to hit main memory, right? We really only need to hit main memory when we need to. And if you need to hit like someone else's main memory, just forget it. You're not doing high frequency trading anymore. You're just doing regular trading, right? So that's the problem. And so like a part of this is that some firms who are maybe not as like not Citadel and who have the money to throw at this and who have like EE people that just like go there and design for them, they actually have to dive into the schematics of their motherboard, look at, which CPU is connected to which PCIe slot, to which RAM, right? And then make sure that their processes, right, their actual like logic for their code runs on the correct threads, on the correct cores, and the correct CPU to access the correct RAM, to access the correct PCIe slot, right? We're talking about like, this is what my professor for IE 421 did, right? When he was in the industry, he had to actually like make sure that what his code was doing and optimizing for that is running on the correct CPU cores. Even though you have more cores, right, it could be slower, right, if everyone else is accessing each other's RAMs, right? So you want to make sure your code is optimized for that. All right, into the central processing unit. Any questions first for the motherboard before I move on? All right, makes sense. So again, I guess some takeaways, if we have to add that here, is North-South Bridge, old architecture, slow but uniform memory access. We moved to NUMA architecture, which is for multi-socket motherboards, where accessing RAM is faster, but it's slower to access other people's RAM, and you have to make sure that the correct CPU, it takes more time to optimize, right? That's really what it's about. All right, so the CPU, some of you guys have not taken 233, but what you should think about the CPU is that you send some bit like instruction to it. So it's literally just like an instruction that is like zeros and ones, and then it figures out how to execute it, okay? And we can just think of this as some magic hand waving like mouse kind of stuff, or actually not a mouse, or else I'll get copyrighted. But you get the idea, right? Like you just hand wave it and yeah. So here's what CPUs look like. These are actually pretty new CPUs. You can see the information of the CPUs on them. This is a i9 and i5 Intel chip. 13th gen. The K I think stands for it's able to overclock. I don't remember. And then here's a Ryzen Threadripper. The Threadripper, you don't see the size, but I'm sure the Threadripper is roughly like 1.5 times the size of these CPUs. It's actually pretty big. It's chunky. It actually uses, for those of you guys who don't know, it uses chiplet design, I think, and then also like, what is it? What did they call it? Like 3D memory or something, 3D something. So it's faster, but you don't have to know what those are because I don't even know too much about what those are. All right. But what you really care about what's under the hood here. And here's an example. This is not that chip, unfortunately. This is the Intel Nehalem chip, which was, I think, in 08 or 07, I want to say. Oh, no, yeah, something maybe 011 or sorry, 2011. I don't remember. But this is an example of the new system on chip, which I think started with Nehalem, right? And here, right, it used to be that the CPU was just the core queue or whatever, right, to like schedule your tasks, and then maybe like L3 cache, right? And we'll talk about caches in a second. But with the new system on chip design, remember, we don't want to access the North Bridge, right? We don't want to go through some like separate like chipset just to access our memory. That's slow, right? We want to beat that. So what they did was they incorporated like memory controllers on the actual die itself. Like this is the actual CPU die, right? It's a 4-core CPU. And the memory controls up there, right? So that actually will control the RAM. So the core can directly talk to the onboard memory controller, which will then talk to the RAM much faster, right? Which is a sort of development of the NUMA architecture as well. And then you have QPI 0, QPI 1. That's probably for talking to different CPUs. They use QPI. It's now called UPI interconnect, like something path. And then there's a new one that's coming out, CXL or something, but you don't have to worry about that. And then MISC IO, I guess they just put some like, probably just PCIe there, right? So let's say you need to access something on your network card or your graphics card, right? How do you do that quickly? PCIe, right? So go memory, core, MISC IO out to graphics card, right? That's how it's much faster. You don't have to go like, North Bridge back to CPU to North Bridge, South Bridge to graphics card, right? We're talking about like reduction of hops as well as massive reduction in latency, right? And here, because we're going to be talking about cache in a second, I want you to see like this is the big L3 cache. I don't know how big, maybe like a couple megabytes at least. You can see actually each core itself has a smaller cache. It's actually like right there, right? That's the smaller cache, and then right above that, I think, is the one of the L1 caches as well. I can't really tell because it's so pixelated, but right, L2 caches are basically a smaller subset of the memory that's in L3 cache usually. And we'll be talking about what that looks like. So, yeah, the big takeaway from this slide is we're moving towards system on chip architecture. Okay, system on chip is much more powerful technically, but also requires more work to think about. Right. Okay. So here's caching. You can see sort of how the caches are laid out. I believe this looks like Intel, right? Or sort of what like an Intel. I don't know about the Ryzen one. I don't know anything, but the Intel one sort of looks like this. At least I can say that. So right now, everything up until the memory controller is on the CPU die itself, right? We got level 3 shared memory controller, right? CPU die itself, and then you have to go out and access RAM, right? Each level 3, you can see there's a level 1, level 2, and level 3 cache. Caches are subsets of memory, right? And each CPU core will do the work. And usually they will, go to L1. If they can't find it there, we call that a cache miss. They'll move on to L2 or L3. And there's like a cache coherency problems as well, right? With this kind of architecture. Cache coherency means, let's say CPU core 1 and 2 are working on the same problem, right? Same subset of data, but CPU 1 changes it, right? Doesn't that also mean CPU 2 needs to change it? If CPU 2 doesn't change it, then it will be working on bad data, right? Does it make sense? So there needs to be a way for CPU 2 to update. And so there's like a protocol for that. I think it's called MESI. It's like, you basically, if everything's read only, but if you write to it, first you have to make sure it's exclusively yours. Then you can write to it, and then you have to overwrite all the other caches, right? If it's in there, right? And there's a way to do that. Although I'm not sure actually how it's implemented on the computer architecture side. I just know it's a thing. And they cover this in 233, right? And so this is hierarchical, right? One thing to note, and I don't talk about RISC and CISC here because this is really just like from an architecture's point of view. But I just want you guys to know that right now in Intel chips, the L1 instruction cache actually like converts the RISC into CISC. For those of you guys who know what that is, okay? And so Intel chips actually, like the CPU cores actually itself run on RISC. It's just that the L1 cache, the L1 instruction cache actually converts it to the CISC from the RISC. Or sorry, converts it to the RISC from the CISC. Oh my God. All right, so here's some takeaways for the CPU, right? It's that CPUs are very good for serialized tasks. It's not really that good for parallelization, but we do incorporate parallelization. I'm going to mention SMT, but I'll do that right now. So basically, each CPU core has one thread, right? Like a worker, right? You can think of it like that. But with the advent of a simultaneous multi-threading, which I think was also like maybe 10 years ago or a little bit more, or Intel's hyper-threading, which is their trademark name for the same thing. Each CPU can actually have two threads, or well, technically more than two threads, but everyone only does ever two threads. And this means that, well, you can think of a thread as like a CPU core, okay? Just think of it as CPU core. So even though you have 4 cores and 8 threads, just think about it as having 8 CPU cores. That's what we call logical cores, okay? And if you were to execute some piece of program, let's say you're password cracking, okay? And you divide the domain of your password into 2 slots, right? The first one you assign to one CPU core, the second one to another CPU core, right? Then you can run those in parallel, right? That's like a perfect example of running something in parallel, right? Password cracking, cool. But what happens is you can actually, by having more threads, I can actually, instead of having 2 cores, 2 threads, I can divide it into 4 spaces and run 4 things at the same time. And this works if and only if the 2 threads that are on the same core, the same physical core, are not accessing the same CPU resource at the same time, right? If you guys both need to access, I don't know, some memory thing or whatever, right? Then it can't, right? Then it'll like be blocked, and then it'll do that first, and then you can keep going, right? That's sort of the idea there. But for the most part, okay, you can treat it as, even though you may have, let's say, a 4-core CPU, if you have SMT or hyperthreading, you have 2 threads per core, you essentially have 8 logical cores, right? Your OS just thinks it has an 8-core computer, right? That's what it is. And if you guys want to see that, if you guys have Windows laptops, you guys can go to Device Manager. I forgot what the Mac one is. And you guys can see that you guys actually have double the amount of cores you have in your computer right now. Even though you might have like an i7, i5, right? You have double the amount of cores. Okay, so that's what SMT is, and that's what logical cores mean, okay? It's just really an abstraction of the physical layer. And then the third thing is that we've moved to SoC, right? System on chips. The O should be not capitalized, where memory, PCIe, and even like ultrapath interconnect, right? Which is a connection between like different CPUs are on the same die, right? So this makes it so that it's much faster, but it also means that you lose a little bit of modularity, and that you have to design motherboards specifically to support some of these functionalities, right? Yeah. All right, so RAM, very important. Think of, if you don't know what RAM is, just think of it as scratch paper, okay? That's literally what it is, but the problem is that you throw it away at the end of the day, okay? That's the only thing. So here's an example of static RAM. So there's 2 kinds of RAM. We're gonna be talking about static RAM and dynamic RAM. Static RAM is basically memory will persist as long as power is applied, okay? So as long as we feed this this block with voltage, right? Then, or with power, I should say, then it will actually like maintain its state, and then it can record the like 0, 1, right? That's it, the state it's at, right? However, as you can see, right, it has like 6 transistors, right? Each of these are a transistor, right? 6 transistors. And also this one has 4 and 2 resistors, although I believe there's a trade-off between the resistor and the transistor, right? So it has 6 transistors. Keep that in mind because we're going to be talking about dynamic RAM, which has way fewer transistors. And so thus you can fit more memory onto a single chip, single die, right? So 6 transistors there. Again, static RAM, remember, as long as power is supplied, it will maintain its state. And contrast that with dynamic RAM here. Dynamic RAM does not maintain state as long as power is supplied. Every single time it needs to refresh. So I don't know if you guys are familiar with like high school physics or EE, right? But so a capacitor is basically just an electrical component that stores charge. However, that charge will dissipate, right? So what you do is you have to refresh that charge every so often, right? And make sure that, if it's a 0, it's fine. If it's a 1, it actually needs to get refreshed, right, so to speak, right? But the new architecture here, right, has only one transistor and one capacitor, which makes it so that each sort of block is much smaller than the SRAM counterpart, and thus you can fit more memory onto the actual die itself. So this is what everyone uses nowadays. Actually, they use the next one, DDR, but I'll talk about that in a second. It's roughly the same idea, right? So you get like at least 4x more additional memory storage. You have some overhead, but that overhead is much it doesn't even matter compared to like the amount of storage you would get, right? But you have to constantly refresh it. So that actually takes up like time. And also there is actually some non-determinism involved with that. So if you're, for example, if you're refreshing and you try to access that memory at some time, then you don't know what you're gonna get, right? It depends. So you have to be careful with that. And exactly how this works, unfortunately, I'm not an EE major. This is definitely within the EE space. I'm talking about I think your FPGA class, I forgot which one that is, will tell you guys this, or maybe EC 210, I think, talks about this. Don't quote me though, because I'm not an EE major. But yes, and so how will this affect order book building? So if you guys don't know order book building, just think about if I place trades, right? How do I keep track of them, right? The problem is that if you're doing something at a low latency, high throughput, right? You actually may encounter this problem. So you actually want static RAM, right? You don't want dynamic RAM where you're trying to change things really quickly and update everything, and suddenly you're hitting something that is wrong, right? So that's really bad. You definitely don't want that, and that I probably don't have to stress how important it is not to have any problems for order book building, right? So yeah, cool. SDRAM is just synchronized DRAM. So if you don't know, it used to be the case where dynamic RAM had its own clock and the CPU had its own clock, and they were different. And so it would actually be slower, right? Because you'd have to match it and then it'd have to propagate. But for synchronized DRAM, it actually now matches the computer. So in your BIOS, I think you can just set it and then it'll do its thing. Yeah, so DDR, which is also DRAM, it's just the DDR stands for double data rate. This is what everyone uses nowadays. DDR, it was what, 2000s, I think, maybe. DDR2. Now we're at DDR5. Your computer should at least have DDR4. If they have DDR3, you should look to upgrade. But yeah, so DDR4, DDR5, you can just see the schematics there. It's roughly double as fast. Each generation is around double as fast. You get a little bit more density, right? I guess DDR5 in this, I don't actually know if it has on-die error correcting. It probably does. There's some additional thing they added to DDR5 to make it so that it's you can have these higher throughputs and maybe error correcting as well. But we're not going to talk about that. Okay, double data rate. And then so how it gets to double data rate is it transfers on the rising and falling edge of the signal. What does that mean? Well, I'm just going to go to this right here. This is a good picture of what's going on, right? So SDR, right, single data rate is just one rising edge. This one is rising, falling. It does reads or writes, right? And then QDR, which we'll be talking about in a sec, has two clock lines for different things. So QDR stands for quad data rate. It's actually an SRAM. It's not DRAM. And this is what's predominantly used for any memory important application in high frequency trading. So if you look at your network cards, FPGAs, or even they actually sell QDR systems on a PCIe slot that you can plug into for trading, right? This is stuff you can do. There's not a lot of information out for this one, public. But yeah, all you need to know is this two clocks, one for read, one for write. It's got high throughput, but it's expensive, right? That's about it. Nova Sparks here, there's a link you can look. They actually sell a system for a ticker plant. I believe they use QDR. They don't mention it, but I think my professor said that. So just wanted to let you guys know. So here's some takeaways. The only thing I guess I want to mention, sorry. was that, oh yeah, error correcting. So I'm going to mention error correcting real quick because it is somewhat important. So you actually like from Cosmic like Razor, well, not really, and from some other applications, right? You may get like a bit flip on your RAM, right? Again, this is all like metal stuff, and you're reading and you're assuming that the actual like electron, so to speak, does not change at all the next time you read it from when you put it in, right? So to speak, right? But it might. That's not a guarantee, right? And so you actually need to like some RAM, especially like like important memory, like applications on like servers or whatever. They usually will use ECC, which is like it adds error correcting. So it actually makes sure that like it, you know, when you write it and what it actually becomes is going to be the same. So I'm not sure exactly how that schematic works, but that's the idea for ECC. It looks like DDR5 will support it, which is like cool, but usually it's not it's like it is a problem, but it may be like like if you run like a server with a lot of read writes or something, maybe like twice a year or something. For like twice a year, you might get like one instance of like 1 bit or something. Right. It is a problem, but it's not huge. But you know, again, if it's like memory critical, then you don't even want those two. You want 0, right, per year. All right. So here's some takeaways there, right? Again, I know I had a weird order. I was thinking about how to do this, and the order I put it in was like in the order which they were created, so to speak. But there's two kinds of RAM, DRAM and SRAM. Those stand for dynamic RAM, which is capacitors, has to be refreshed, and static RAM, which is doesn't have to be refreshed, but you can't have as much memory because it has more circuitry to go deal with the staticness of it, right? And so there's you know, DDR, which is what everyone uses, and then QDR for SRAM. So those are really the two predominant areas of RAM there. And everyone uses DRAM because it's highest memory capacity. We're talking about like 128 gigabytes, right, total in your computer. So like you know, 32 gigabytes on a stick of RAM, right, both sides, right? That's pretty good. That's pretty crazy. QDR, not as much. I believe it was like megabytes or something, which is like fine for certain applications. But again, they're expensive. So scaling to that gigabyte thing is going to be pretty hard. And then book building, right? Any memory critical systems will use probably QDR, right? And it's used on NICs, which are network interface cards for data throughput, okay? So we're going to talk about that. First, we're going to have a quick segue into GPUs because GPUs are, you know, everyone talks about them nowadays, but they're not actually really used too much in HFT. Probably in some applications of heterogeneous computing, but I don't. Yeah, like if you think about it, there's not really any like specific applications for this. So the difference between, okay, I should start by describing the GPU. There's the RTX 3090, came out like 2 years ago. Pretty cool. I think it's Ampere architecture. I'm not sure. I believe this is the Ampere architecture. What it looks like here. And that's what the chip. If you remove like the fans and the metal plate, I forgot. Yeah, the cooler or whatever. Then you're left with that. And so if you look here, each one of these is basically like a graphics core, right? So you have a graphics core with like different workers, right? And then those, access like the memory here, and those access like you have an L2 cache here. NVLink is for connecting to another GPU, I believe. And then, yeah, I can't see what this is. HDMI. Oh, this is probably like output. Yeah. So graphics cards are really they're originally used for drawing like graphics intensive applications, right? So we're talking about like, if I take a picture, right, how does it actually render everything, right? It has to actually calculate like the intersections, has to calculate maybe lighting, has to calculate, basically it has to convert from what the game sees and the game information to the exact pixel on your screen, right? What is that pixel going to look like? That's what it basically has to do, right, roughly. So with the advent of ray tracing, which is where you basically can get reflections because it actually calculates sort of the reflectiveness of like surfaces through like rays and traces those rays and figures out the sort of power, right? Or how much like color it should, that surface will, what it's reflecting off of will convert to that surface, right? Then it will actually do some calculations there. So Intel came out with like a new chip. I forgot, what is it called? 770A something, where they actually have like, NVIDIA has specific ray tracing chips where the architecture of the chip is specifically accelerating ray tracing applications, right? That could be, I think it was some like intersection thing. But I'm not a graphics person. I'm not a GPU architecture person. So I cannot tell you too much in detail what it is. But that's the idea, right? You can actually create like different cores that specialize in certain applications to make those applications faster, right? I'm actually going to talk about some of the stuff like that. So that's what GPUs are for. They're very good for machine learning because machine learning is all about add, multiply operations. You multiply something and then you add next, multiply, add next, right? And they're sort of independent, right? At least between layers, right? They're independent. So it's a lot of matrix multiplications. And so GPUs are great for that because they already do the same thing with graphics, right? GPUs are really focused on cores that can, like a lot of cores that are small, right? So they can't really do what a CPU can, but because there's a lot of them, they can do these applications really quickly, right? That's really high throughput, sort of the idea there. All right, so here's some takeaways for GPU. It's really, really only for massively parallelized computation, right? So take your password cracker, for example, right? Remember how we split, like, let's say you had, I don't know, 10,000, right? You split into 4 pieces, 2,500 each, right? To a CPU thread. Why not just have 10,000 cores and give one to every single like part, right? For example, that's like how you would parallelize, right? So that's what makes it highly parallelizable. Although it may be slightly slower, right? It won't be that much slower because you can do way more, right? So the overall time is going to be condensed as long as your GPU can actually do that, and it doesn't have to do too many calculations to do that, right? So hashing might take a hot second. I think actually GPUs did have like a hashing thing, like core specifically for hashing, which is like good for encoding. I think like similar to memory encoding and hashing, they had some like cores for that, and so that may have been part of the architecture, but don't quote me. That's why it was used for like Bitcoin mining, right? Highly parallelizable, and maybe even some cores that are specialized in hashing specifically, right? But they moved to something called ASICs, which we'll talk about in a second. And the only other problem is that memory needs to be sent from main memory to GPU RAM, right? So if you're doing machine learning, right, this is a huge problem, right? Your model can maybe even barely fit on your GPU's RAM. We're talking about 12 gigabyte model. That's pretty on a low end, right? And then you have to transfer the data that you'll be training on from the CPU to the GPU, right? That takes time. It's a bottleneck for training, right? So that's that. For high frequency trading, I believe it's really just mainly for like visualization tasks, maybe that you would do something like this. I don't know too much about, I don't know of any specific applications where GPU is like directly like the first thing that comes to my mind. Yeah. Any questions so far? Sorry, I forgot to pause and stop. We're great on time, so we're nearing the end of this presentation at least, but we can talk about some other stuff. All right. So storage. Storage is the other important part of your computer that you need to know about, right? So this is what it used to look like. You can actually still buy these. I actually bought a computer like, I want to say 6 years ago that actually like came with one of these. Like, bruh, why are you so cheap? But anyways, hard drives is what we used to have. It's literally looks like that inside. It's a spinning disk with, we call those, I think, arms, right? Where they actually read and write onto that disk using magnetization, right? So there's like a small film of something like a film of something that's magnetized, and you just, depending on, apparently I think this is the encoding. I got this from Wikipedia. So pretty cool, pretty interesting. But it's very slow. Really, like at the end of the day, this is just cheap to make, but slow. This is super easy to make. The reason why it's slow is because you have to wait for the disk to come around if you miss it, right? So that's some latency there. And then also uses magnets. So if you have like a big neodymium magnet, right, and you sort of like brush across it continually, right, it'll eventually kill it. It'll corrupt the actual like the memory on that disk, right? But apparently, like you actually need like a pretty powerful magnet and like a decent amount of time before it'll actually kill itself, which is like cool. It's very slow, like incredibly slow. These run off of SATA, the SATA bus, which is what I showed you in the motherboard. which is slower than PCIe, but these can't even like make use of the entire SATA thing, right? They're that slow. They actually have to like move the arm, wait for it to rotate right back to the correct, and then read it and then like magnetize it. It takes a lot of time. And apparently there's not a lot of storage. So this is the highest hard drive that was ever made in 2022, I think, 18 terabytes. It's like, that's a broad moment right there. So literally the only reason you would use this is because it's cheap. That is it. I don't think you would use it for anything else. I can't think of a reason you would use it for anything else. So just don't. Yeah. However, here we have what everyone uses nowadays. Like every single one of your computers use this kind of technology. It's SSD. SSD stands for solid state drive. So it uses NAND flash, which is like a type of flash mechanism. I guess I don't know too much about that. I have a picture of the architecture here, but I am not a E major, so unfortunately I cannot tell you exactly too much about what's going on here. But really the gist of it is that for persistent memory, right? Instead of doing magnetization, you store it in something like that, like an array, and then it's just electricity or something else. Maybe it is also somewhat magnetized. I actually don't know. Anyways, it's some type of flash technology. There is a M.2 form factor. M.2 form factors are sticks. So I can actually maybe pull up one and show you guys. Yeah, so there you go. All right, let me just make sure that I'm showing the right screen right time. All right, so here's what the new SSDs looks like. This is all in your computers nowadays. It's a M.2 form factor, right? It's actually much smaller. We're talking about like in my hand, it'd be like this small, right? Whereas the other SSDs are like this big or like thick, right? But they store more. Here, the good thing about this is that not only are they small and they store a lot, like this is a 1 terabyte drive. This is actually what I have. I think maybe it's maybe it's the other one, not the Pro, on the 970 because it's cheaper. But they actually run the memory through PCIe over something called NVMe, which is non-volatile memory express. They run it. That is actually another protocol on top of PCIe to enable you to actually access the memory via PCIe, which is really fast. Okay, we're talking about like gigabits per second fast, right? So that's why people use M.2. That's why your computer uses it. If you guys still have an old computer lying around, you guys can actually try booting into like your Windows or whatever, and like booting into like your OS, and it'll take forever with a hard drive. But with these, so a hard drive takes me like 2 minutes when I had one. These ones take me like 10 seconds, 5 seconds. Yeah, that may just be Windows doing Windows things though. So, right. And so that's actually what we have at Quant. We actually bought like an 8 terabyte like SSD for some reason. I mean, it's for a project. Okay. So hopefully Source doesn't, no, I'm just joking. The problem with SSDs, even though they're amazing, is that they have a limited number of writes, but I forget what this is for, but they have around like, this is stands for 600 terabytes written. So you can actually read, write, right? For 600 terabytes before it'll stop. But this is actually what's listed on the manufacturer. What actually happens in real life is probably like double that, right? Or quadruple that. So you're never gonna really see that unless you're running a server, right? Maybe for HFT application you might, but I mean, for HFT money grows on trees, right? So you just take it, buy it, another one, stick it in. And then so they slow down as they reach full storage capacity, which was interesting, but I don't exactly why. It might have to do with like how it actually like reads or writes to that space. And they are pricey. They're 5 times as costly, and this is probably on the average side, 5 times as costly as your hard drives. But like, if you're here for HFT, right, you don't really care about the price. It's sort of like, yeah, it's just like, oh, I guess. And so lots of storage. 100 terabytes was also what Wikipedia showed me for current 2022. You can buy 8 terabytes, which is what we have. We have an 8 terabyte right SSD. That's not something that you would really trust a hard drive to do, right? And hard drives, if you open it, you shake it and it scratches something, it's dead. You literally, it might look fine, but it's dead. You can't do anything with it. right? So that one is specifically a SATA SSD. So it actually does go over SATA, which is slower, but it's fine if you don't really care because it's bigger, right? It just stores more. But for like any memory, like high throughput intensive applications, just use an M.2 like NVMe SSD. Just stick it in there. Some people actually probably have SSDs that are NVMe but not M.2, so you would stick it in one of the regular PCIe slots. Okay, I'm sure that exists, but motherboards usually, like if you look at the very start, right? Motherboards already have an M.2 right there, right? For you, there's 3 here for this motherboard I'm looking at, right? Just use those, and then maybe you might need more storage, but I doubt it. Right? If you need to use other storage, you might as well just like have it somewhere else or do something else with it. Right. Okay. Cool. Storage. That was storage. So we're gonna quickly talk about other types of chips. So this is pretty much it. The end of the presentation. So there's 3 things you have to know: FPGA, ASICs, and NICs. FPGAs are aptly named field programmable gate arrays. And what those are is they look like that. They look basically like a copy paste array thing, which makes sense because it's an array that's in the name. But what really you use them for is that if you can code something in Verilog, you can upload it, or you can like write it to the thing, and it'll actually like create those electrical connections that match what you wrote in Verilog. Verilog is a hardware description language. So for example, right, let's say you were to make an AND gate, right? An AND gate is basically just like, I think it's like probably 2 transistors or something like that. 1 transistor, I don't know, I don't remember, right? And that basically, you have like 2 inputs, and then you do something, and then 1 output, right? And so that's an AND gate. And so you could just code that here, and it will actually configure these such that it'll actually do that. So I don't know what's inside each programmable logic block, but you get the idea, right? And so if you wanted to do maybe a adder, right? An adder is just like, I think 3 gates or something. Then you would just write it in Verilog and then put it in here, and then it'll do it. So it seems like very hand wavy right now. We treat it like it's hand wavy, but if you code in Verilog, if you take CS233, it'll make sense. Okay. What's good about FPGAs is that you can actually code them for a specific application. So let's say, and they actually do this, there's a company that sells this. You will have to check whether or not the order you send out to the exchange makes sense, right? Maybe you have to make sure that, I don't know, your trader did not, butterfinger in a trade. Instead of putting it at, 100 shares of Apple or $100 of Apple, they put like $1,000 like buy order for Apple or something like that, right? Pretty bad. And so maybe you might want to create an FPGA that deals with that, right? So it makes it so that it doesn't, for whatever the current price of Apple is trading at, it doesn't actually, whatever trade you put into the exchange is not, more than or less than 20% of the current price, right? You can code that with an FPGA, and once it receives that order, it checks that with some logic that you code in like hardware, so like an AND, OR, NOR, XOR, NAND gates, right? That's how you would do it. And then once if it is bad, right, you can just corrupt the frame of the Ethernet frame that comes in, and then when it hits the exchange will reject it because it's corrupted, right? That's an example of a bump in the wire scenario, right? You want something that executes maybe less than like 10 nanoseconds or something like that, right? It can probably do that depending on the clock, right? So it's very fast, very quick, very efficient. The only downside is it does have a slower clock cycle than the CPU, but it could run faster than the CPU because the CPU has certain overheads, might need to access something, right? So the FPGA could be better, or usually is better actually. It is pricier than the CPU. The CPU is actually pretty cheap, maybe $200, $300. FPGAs can go way more. And so here's some examples of different people's FPGAs. I think that's like Broadcom, Xilinx, and Intel's. I forgot what their division for FPGAs like. So it starts with an A something, right? And so this is basically like how they outline the FPGA. So an entire FPGA board, in this case, let's take the Xilinx one because Xilinx is ubiquitous in HFT. They have like a network interface, which is just the 2 Ethernet ports for 10 and 25 gigabit over Ethernet, right? Flash for basically you send something to flash and it'll flash the board for what your or like a Verilog hardware description language, HDL will say, right? And then here's how it receives the data or whatever sends the data to the computer, right? I guess you have an Ethernet controller and I guess some RAM here. In this case is DDR RAM, right? But you could have QDR RAM there as well. Yeah, I don't know too much about the architecture for this, but that's sort of the idea. Just the general gist of it is that FPGAs you can design for specific applications, and they're usually much faster, much better. Yeah, but it could be slower, right? So in this case, right, you could use CPU to check if a price is valid, right? But you might have to like go and actually like do some logic on the CPU itself, and then like send that to the network. Whereas this one is just like literally it's a in and out scenario, right? For the CPU, it actually has to like maybe cache something and then like take it from memory and then look and then do some computation and then output it. Here's the same thing. But because you can explicitly design the architecture so that it bypasses some of the things that the CPU may have to do, right? Then you don't care. It's much faster that way. So really it just comes down to the CPU is a specific implementation of the silicon, right? An FPGA is a sort of templated silicon, right? We still create a design, but the design is such that you can actually create different architectures with it. So you can actually make a software-defined CPU, right? And then like put in ACL and like Verilog, and then put it on the FPGA. So you can actually run like CPUs on the FPGA itself, right? Because it follows the same architecture. But with a CPU, you can't change anything, right? Can't even look under the hood. With FPGAs, you can. You can even change it to another CPU. You can have put two CPU cores on here, right? If you don't want the memory controller, you don't have to, right? Use that. There's a lot of like freedom to it, and that's why it makes it faster, because you can actually like optimize for it. Okay. So, all right, ASICs. ASICs are basically chips designed specifically for one application. Okay. CPUs, you can argue that yeah, they're sort of like ASICs, but really CPUs are very generic. They can run any type of task. So we don't call them ASICs. They're really just CPUs. A GPU is the same thing, although it's for graphics applications. We don't really call them ASICs because, again, for any graphics application, they can even be for machine learning, which is entirely not graphics, right? But take like Bitcoin mining. So you may have like literally an architecture that only does hashing, right? And that's all it does. And you just like group them together and basically make a GPU, but for hashing only, right? That's an example of ASIC. So that's what ASICs were used for. That's why they're prominent now. It really was because of Bitcoin, or like I should say cryptocurrency, like proof of work, hashing, or verification. I forgot what it's called. I'm not too familiar with blockchain. But in the HFT industry, you may use it for certain things. Let's say order book building, right? But the only problem is that ASICs are very, very costly to manufacture. We're talking about like 10, 20 million, right? Just to get the first die out. And it costs cents on a dollar just to get like more, right? So if you want to buy like the problem is like the first one might cost like less than 2 million, right? And if you buy 1,000 of them, right? Even though it costs 2 million to make the first one and like 10 cents to make the other ones, right? You're probably still selling them for like $2,000 each, right? Just to like divide up the cost for manufacturing it, right? And that I don't think that even includes builder researching. So it's very expensive. And you'd actually have to find like a chip manufacturer that does that for you, right? So annoying. Yeah. So most people don't do this unless you really need like that latency. And then next aren't really too much. I guess there's a bit more to them, but I didn't put them in the slide, which is that they're just network interface cards. They're important because that's how you talk with an exchange. That's how you get high throughput. I'm not too familiar with them. They do have like, I believe, separate clocks. That's how they get the higher Gbps. And so you just need to read and write or read from them like decently fast enough, I guess, to make use of that. They can do 10 or 25 gigabits per second. I think it's gigabits over Ethernet or something like that. And that is just like probably you won't usually see 10 or 25 on a wire. It would just be on the high end, right? You may get bursts of up to that amount. So yeah, and then next, I guess, and this is a bad example, but they also do sort of look like this. Okay, they have like the ports for the Ethernet, and yeah, that's about it, I think.